Okay. Good morning. So last day we did, so I'm still waiting for that question from Kieran Preet. I don't know if you wanted to talk about it later or what, but okay. So last day, right, we talked about, well, what did we do? Oh yeah, we talked about functions. So for review, oh, and a little side note before we get started, I bumped some of those assignment due dates. X to the power of, and then what's the question? Solving for x or? So I'm seeing, I presume x to the power of 4 minus 6x squared plus 2 equals 0. Find all real solutions rounded to 2 decimals. And which section is that from? Oh, sure. Okay, so, and did I copy out the question correctly, Karen Preet? Oh, it was from the homework. Okay, so for this one, so something like maybe 1.10. Okay, I'll just make this part of our review. Sorry, I wrote it so sloppy there. There. Okay. So for this one, I mean, I won't get you to do one of these kind of by hand. I would probably just use Desmos here, because what you need to remember is that if you want it to be equal to 0, right, it's equal to 0 when, let's think about this, right? So here's my x-axis, here's my y-axis. When is this equation equal to 0? Well, if this equation is equal to y, it's when y is equal to 0. Y is equal to 0 here, right? Y equals 0 on the x-axis, right? And so the solutions to this thing are going to be when it crosses the x-axis, right? And so the solutions are the values of x where x to the 4th minus 6x squared plus 2 crosses the x-axis, right, where y is equal to 0. Okay, so because I'm not getting you to solve this one, this feels like a 1.11 question where we should be using Desmos, because a lot of them are a little bit harder than, like this one, I wouldn't get you to do this by hand. Okay, so if we put it into Desmos though, x to the 4th minus, sorry, I'm just trying to remember the function, x to the 4th minus 6x squared plus 2, okay. X to the 4th, step it down, plus 6x squared, step it down, plus 2. Sorry, minus 6x squared, I think. Looking at the chat there. Okay. So it looks like we've got, oh, I'm going to zoom in here, right? So it looks like we have a couple of different solutions here, right? So when x is negative 2.376, and then when x is negative 0.595, positive 0.595, and positive 2.376 in this case, right? So I would just graph it in Desmos and and grab those values from there. So in Desmos, we find that we have something that kind of looks like a W. Like that maybe. And this was at negative 2.376 and 0, negative 0.595 and 0. And then here, these are the positive versions, 0.595, 0, and 2.376, 0. So your solutions then are going to be these values here, and it should accept the decimal versions. Yeah, so all of these are the answers. So x is equal to, the solution is that x is equal to negative 2.376, negative 0.595, positive 0.595, and 2.376. Usually it wants it entered as a comma separated list, which would be like this, right? And usually they have it set up so that the x equals is on the outside, so you shouldn't be putting that in, just the answers. So these are all the real solutions. Good. Okay. So so x squared minus, yeah, so that's going to be the same, right? So except you want to restrict your domain to the negative 2 and 2. So one thing you could do is, if I were to do that here, negative 2 and 2, well, one thing I could do is, if you wanted to, you could say x equals negative 2, right? So that's my cutoff point. And then x is equal to positive 2. That's my cutoff point. Another way you could do it is, I think in the little wrench up at the top, you can do something like, here, you can change your x-axis from negative 2 to positive 2. It's just saying restrict your vision to be between negative 2 and 2. Makes sense? Awesome. Great. Great. Okay. So last day, last day we talked about, we finished up with lines, and then we kind of went into functions, right? So we talked about functions, we talked about function notation. So f of x is function notation but we did, and I want to highlight it again, right? Whenever you see f of x, you can really just read it as y, right? It's some output. So we've already seen functions, we just haven't called them functions, right? Read it as y. And then we talked about the domain of a function. Okay. I'm having a hard time not just redoing last day. I don't want to do that because we already talked about it. Yeah, there was some nitty-gritty stuff like, okay, so how do we read this thing, right? So f takes an input of x. And then we even talked about kind of difference quotients, and those will come back up. So I'm not going to review them as much, but and then we talked about the domain of a function. And what do we need to remember about the domain? For now, we only have two things we need to remember. We need to remember we can't divide by 0, right? And we can't take the square root or the even root of a negative number, right? And so here for our domain, and I say two things because later on, once we get to chapter 4, we're going to add a third thing. Okay, so for now, there's only two things, but just be prepared to kind of open up to have more restrictions on the domain. So can't divide by 0. Can't divide by 0. And we can't take the even root of a negative. What does this translate to? When you see a function and I ask you to find the domain, it means you're going to scan this function. Is there any division? In that case, I need to make sure I can't divide by 0, right? I need to pull out any values of x that make me divide by 0 from the domain. And are there any square roots? If not, great, right? If there are, then I need to make sure that I'm not taking the square root of negative numbers, okay? So let's do another example of these guys here. So I think we did 65 already. So we did 65 last day, okay, which had, of course, both the square root in the numerator, but also, of course, if there's a numerator, there's a denominator. So then we were dividing. So we had to kind of find the overlapping domain, right? Which is we can't divide by 0 and we can't take the root of a negative number. Okay, so let's do 70 because I want to have the root in the denominator and see how that kind of plays out. So let's do 70 for review. So I have f of x is x squared over the root of 6 minus x. Okay. So I have division, right? And I have a square root. So I need to make sure that I'm not dividing by 0, right? And I can't take the root of a negative number. But because this square root is in the denominator, what I can do is I can just add the restriction that, well, this square root can't be 0. In general, I can take the square root of 6 minus 6, right? Because the square root of 0 is 0. But in this particular case, right, I want to exclude the 0 from my domain. So here, we need to make sure we exclude values of x from the domain that make 6 minus x less than or equal to 0 and the root of 6 minus x equal to 0, right? So what does this amounts to? So in general, right? Therefore, overall, we need, 6 minus x to be greater than 0, right? I need to not take the root of 0 because then I'm dividing by 0. Okay, so that takes care of that part. But then I also need to make sure that 6 minus x is always positive because I can't take the square root of a negative number. So here, you have to keep track of. So sometimes I'll talk in the kind of pros and cons list, right? So here, this is something that we want to avoid, 6 minus x being less than or equal to 0. We can't do that, right? And we can't have the root of 6 minus x be equal to 0. Here, I'm talking in the positives, right? In the sense that, okay, I need this to happen, right? So you need to be flexible with how we phrase things, right? And so, but I know that can be confusing, right? But with practice, it'll make sense. So here, we want to make sure that 6 minus x is greater than 0, which is going to satisfy all that criteria. So 6 minus x being greater than 0, remembering how to work with inequalities, right? So the only restrictions where we can't treat an inequality as if it's an equal sign is if we're multiplying or dividing by a negative number. Then we need to switch the direction of the sign. In this case, if I do a little, if I add x to both sides, then I don't need to deal with that, right? So then I get 6 has to be greater than or equal to x, which usually we read it the other way around, right? So x has to be less than 6, right? I always want you to kind of imagine the answer going in here, right? Does it make sense? So 6 minus something less than 6, so 5, for example, that's 1, the square root of 1, it works, right? And so I just want to make sure that what I'm saying down here actually works up top here, right? And we have that benefit of being able to check our work, right? So I don't want you to give me an answer that doesn't make sense, right? So the domain then, the domain we decided is all the x's that are less than 6, right? Meaning I can go from negative infinity up to 6, but not including 6. So I do a round bracket. Okay. Good. Nice. Okay. Let's see where my page break is here. Way down there. Okay. All right. So, talking about functions, in section 2.2, we're going to talk about some graphs of functions. Now, let's see here. Do I want to put it on a, sure. 2.2, I'll put it on a fresh page, how about? 2.2 is called graphs of functions. Okay. So from section 2.2, there's a big kind of summary piece, and it has a bunch of different graphs and functions that we should kind of be familiar with. I'm not asking you to memorize them. I'm not asking you to you know, do anything, except we're just going to talk about them, and then being able to recognize them as they come up is going to be really useful. So, so for a graph, okay, what we need to think about is that, okay, so I've already assumed that you know a little bit about ordered pairs, right? So a graph of a function, and maybe I'll nab this here, is just going to be all the ordered pairs, okay, mapped out on the xy plane. So if f is a function with domain A, so some domain, just like we decided up here, right? So maybe in this case, right, negative infinity to 6. Then the graph is the ordered pairs x and f of x, right? So x is the x value and f of x is the y value, right? So here, let's just make a note that an ordered pair will always look like this, x comma y, right? Where if you have your x-axis here and your y-axis here. One thing I should mention, because it's pretty cute, I had a student a long, long time ago. I shouldn't say a long, long time ago, maybe 5 years ago. And she just had such a hard time. She goes, I can't remember which is the x-axis and which is the y-axis. And I said, well, it's just x and the y-axis, right? So if you worked with these enough, you just know which one's which. But so she said, so I have to remember it like this. So I just imagine a little guy. And so just imagine here, you've got this little, the x-axis is falling on this little guy down here, and he's going, no, like this. Maybe I'll try to do kind of, no. Anyways, I thought it was really cute. So if you're having a hard time remembering which is the x-axis and which is the y-axis, I think that's probably the cutest thing that I can have heard of. So anyways, I should probably delete this, because if someone who wasn't here for the explanation sees it, it really won't make sense. So, and maybe it still doesn't make sense, I don't know. But anyways, so here, if you've got XY coordinates, then for example, right, so we've got our XY plane here, and we'll just stick in the first quadrant here for now. Of course, the Y goes down to negatives, X's go to negatives, but let's just stay in the positives for now. Okay, so here, if you've got X, and maybe the point is here, right? To map X, Y. And maybe let's put little subscripts on here, X1, Y1. Otherwise it can get confusing. Okay. So I've already kind of assumed that you know how to map points on the plane, but if not, then here it is, right? So you have ordered pairs, and this is an ordered pair, x comma y. Notice that here you have x comma f of x, right? And so, or what we can say, or remember f of x is just y, x or f of x and y are interchangeable, right? So this is the same as x and f of x, right? So here, this is your input and this is your output. Input, oops, and f of x is your output. Okay. So you put in some value of x and it gives you some value of y. Usually functions are more like lines, right? And so we can read that line, we can take some input and read the output, map it back to the y-axis. Okay. So let's see here. Let us if you look at these, okay, notice that it says sketch a graph of the function by first making a table of values. I've actually moved away from that. I don't think that it's very beneficial. We have Desmos, and so what I want you to do is I just want you to enter these. So let's look at, and we already did one today, right? So let's look at the root of x minus 2, for example, right? And so let's just graph it in Desmos and see what happens. So we have the little square root button here, and x minus 2, there. I have to zoom out a little bit. Okay, So notice that here, okay, at 2, 0, oh, sorry, it's lagging. It goes from 2 and then all the x values greater than 2, right? Which matches our domain, right? And so that is what the domain is. It's just telling, okay, what are all the possible x values that can go into this thing, right? And so, and then the graph, there we go. Now it's letting me kind of map out, is giving me all the possible x values, but also all the possible outputs, which would be the range, which we'll get to. Yeah. Actually, it's just on the, oh, it's in the next section. So I'll leave it for the next section, the domain and range. But for now, right, so here, I don't really want you to make a table of values. It's a real waste of time. And honestly, until you know the shapes, so here, these are what I'm going to call the shapes of each of these functions. It's going to be hard to graph with just a table of values. So, but before we go there, I want to talk about piecewise defined functions. So piecewise defined functions, I feel like, yeah, we've already talked about piecewise defined functions, but here, right, so the output f of x is going to depend on which area of x you're in, right? So piecewise defined functions, it can break it up into many different regions of x. And it's just saying, okay, well, this function, it's going to behave differently depending on where you are in your x's, right? So where you are in your domain. So to sketch a graph of a piecewise defined function, what you need to do is, well, you can't really tell Desmos that you want a piecewise defined function. That's okay, because we can graph each of these individual portions of the function, and then we can figure out where it stops and starts. So let's go here. To graph a piecewise defined function, we use Desmos to graph each piece, let's call it, each piece. And then we, right, so on our own, right, we break up the domain appropriately. We break up the domain appropriately. So, for example, if we were to do, and I want to do something that's, okay, maybe let's do 34 to start. So 34, well, if f of x is equal to 1, what does that look like if x is less than or equal to 1? So here, let's write out our function. F of x is equal to 1 if x is less than or equal to 1. Lots of ones in here, so, but it's just our first one. And then f of x is equal to x plus 1 if x is greater than 1. Okay. Notice that all the values of x are defined, right? So here, if it's less than or equal to 1, and here if it's greater than 1, so it picks up just after 1, okay? So what I want you to do here is I want you to imagine your XY plane, and it looks like here at x equals 1, there's going to be a change, right? It's going to be a change in how the function behaves. So here, let's say at x equals 1, let's do a little kind of split here, kind of an imaginary split. So if x is less than or equal to 1, f of x, which is just y, right? So for all these values, up until x is equal to 1, f of x is just going to be 1, right? So here, y equals 1, so f of x is the same as y, so y equals 1, let's say is here. And I shouldn't have drawn that dot there, because it might be confusing. Okay. So here I have this line, f of x is equal to 1. So, and it's going up until x is equal to 1, so I do a closed dot at x equals 1. Okay. If x is greater than 1, so now I'm looking at all of these values here, then y is going to behave like x plus 1. Notice that x plus 1 is just a straight line, right? A y and an x, so we recognize that as a straight line. What I want you to do is, if you had to graph these by hand, which I'm not really going to make you do, you can use Desmos, but this one is so small, so why not? Then what we're going to do is I'm going to plug in values of x that are greater than 1. And remember, to draw a straight line, right, recognizing that this is a straight line is going to be really good. Since it's a straight line, right, I only need 2 points on the line in order to draw it. So I need to figure out what x is. I know it's not x plus 1 at 1, right? But we can do an open dot, right? So at x equals 1, right, x plus 1 becomes 1 plus 1, which is 2. And so here, if we have f of x equals y, which equals 2 at this point here, I'm going to do an open dot, right, because it's not at 1, but of course, x plus 1 is going to be this straight line with a y-intercept of 1, right, and a slope of 1. So many ones in here, it's a little bit confusing, right? So we'll do another one after this, but right, so I know that this line, it behaves like a straight line. It goes from negative infinity to positive infinity. That's not the problem. The problem is that this function has restricted it to only be for x is greater than 1. And so what I need to do is I need to find another value of x that's greater than 1, and then I need to evaluate the function in order to get a second point on the line. So what I'm going to do, I'm going to let x be 2, seems reasonable enough. And let's maybe so here x equals 2. 2 is greater than 1, for sure, right? And so 2 plus 1 is 3. Oops. So f of x equals y, which is 3 here. That's a point on the line, right? So what happens is, okay, so now I can take these. Ideally, I would draw another kind of line or a point there, but I think we get the idea. Okay. So here, this line goes all the way to negative infinity, and then this line it picks up and it goes all the way to positive infinity. Right? So being able to read these piecewise defined functions, we need to be able to do that. This was a nice and easy example, right? So this one, yeah, we can do this by hand. It's just a straight line or a horizontal line, and then just a line with a slope of 1, right? So we can deal with that, right? But let's just see how we would deal with this in Desmos. right? So how would this work in Desmos? So I've got f of x equals 1 and x plus 1. Okay? So what I need to do is I need to have y equals 1, and I'm going to zoom out here till I see kind of x equals 1 on there, because I know that's where I'm going to break off. And also y equals x plus 1. And I wonder if it'll just do, I think it just assumes it's y equals, 1. No, it wants to know that y equals 1. Just play around with it a little bit. Okay, so what we said was, okay, so now we see the behavior, right? Both of these are just straight lines, so they'll keep going. Lines, remember, have a domain of negative infinity to positive infinity, the set of real numbers. So these guys, right, they're just going to keep going and doing what they do. But our function says, okay, here at 1, that's where it's going to pick up, and that's where it's going to become this line. And up until 1, right, on this straight line, that's how it's going to behave up until 1, and then it's going to jump up to be on this line with a slope of 1. Okay. So we did that by hand, easy enough. But you can also use Desmos. So especially for these harder functions, like let's go ahead and try to sketch a graph of, I want to use something with not as many ones. So let's do as many, all of them have ones, but let's do 38, okay? Just having a look here, 2x plus 3, I recognize that that's a straight line. In fact, it's a straight line with a slope of 2 and a y-intercept of 3, right? 3 minus x, I also recognize that it's going to be a straight line, but it's going to be a slope of negative 1, right? So now it's going down, and a y-intercept of 3. So notice that they have the same y-intercept. So we know a lot about this function just right away, right? And it looks like our transition point here is going to be at x equals negative 1, right? And so what we do is let's draw each of these in Desmos. And then what's going to happen is, okay, for x less than negative 1, not including negative 1, right? So open dot here, it's going to behave like 2x plus 3, which would be a positive slope like this. And then at x equals negative 1, it's going to transition over to behave like 3 minus x, which should be a negative slope. So we have 2x, let me just grab it here, 2x plus 3, okay, like we said, okay, it's behaving like I thought it would, right? This positive slope, 2x plus 3. It's just catching up there. And then my second line is going to be 3 minus x. Okay. Again, just like we anticipated, just by looking at those functions, right, they do have the same y-intercept. Okay. And so the point that we're interested in here is at negative 1, right? And so from negative infinity up until negative 1, it's going to behave like this first line, the black line, okay? But not including negative 1, so open dot there. And then at negative 1, let me see if I can pick it up here, negative 1 including negative 1, it's going to behave like this line, right? So after negative 1 on this black line, we just ignore it because for our function, those don't happen. It switches to behave like the other function. So let's see here. So from Desmos, we find that we have something that looks like this, an XY plane. And we said, okay, here, let's put this at, sorry, not 3, 0, 0, 3. Why did I say 3, 0? That would be down here. X is 3 and Y is 0, right? Here, X is 0, Y is 3. So I've got kind of this, oh, maybe I'll use a different color. I had this kind of line here, 2x plus 3. I'm not going to be too picky about, you know, I draw these because we use Desmos anyways. And then we have, oops, it's supposed to go through that. Come on, straighten out. There. And then we have 3 minus x here. Okay, if you could tell me which part of the graph confused with, that would be good. So until then, I'm just going to keep going here. So I'm going to translate this, the x-axis, or the x-intercept, negative 1.5, and let's see here. So this here is at negative 1.5. And so at some point here, x equals negative 1. That's where I'm going to transition, right? So I'm going on this point, 2x plus 3. Oh, sorry, it's lagging. Okay, I'll say that again. So for x's less than less than negative 1, not equal to negative 1, that's when it behaves like this graph, right? And then at x equals negative 1, that's where it switches. And so now we jump up to here, and now it's going to behave like 3 minus x. So our overall graph becomes, let's see here. In fact, I'm going to kind of remove this, put a closed dot here, and put an open dot here. And then I'll just kind of remove this. So what happens is this graph behaves like this. So positive slope, and then at x equals negative 1, it's going to jump up to here, and then it's going to go like this. So our graph looks like this. Looks like this. And of course, you don't need to the arrows, but they do keep going here. Okay. And this is at negative 1. So this is what our piecewise defined. And you can tell, right, these are little pieces. And so it's a piecewise defined function. Does that kind of clear that up, Karen Prater? Great. Awesome. Yeah, so play around with those, and definitely use Desmos, especially for kind of harder functions. I think there's only straight lines on there, but later on we'll move to different functions. So, all right. So like I said, different functions means that we need to know the shapes of kind of typical graphs. Okay, so just like when we see a linear function, right? So 1 y and 1 x, then I know it's going to look like a straight line, right? And very similar to kind of take you back to like way back, right? Not even math, but if you, I guess technically it is math, but if I ask you, what shape is this? You know it's a triangle, right? So just like we recognize these shapes, right? Basic shapes, and we need to be able to recognize graphs, right? So now we're extending, but that's how I want you to think about it, right? If you're able to look at a graph and say, oh, that looks like a quadratic, for example, or, oh, my function is a quadratic, I know in mind what that looks like, right? Or, oh, I have a root, okay? It's an even root, so I know what that's gonna look like. Or if you see a graph and then you say, oh, that looks like a root function, okay? So just like if I asked you, hey, what is this? Well, it's a circle, right? What is this? It's a triangle, right? And so we need to develop that kind of recognition with functions, okay? So kind of start a new part of this here. Just like, oops, we are able to recognize shapes like a triangle or a circle or a square, right? We need to be able to recognize the shapes or know the shapes of some common functions. We need to be able to recognize the shapes. I'll put shapes in kind of quotes. Of course, it depends on a couple of things, but the general shapes will always be the same. Need to recognize the shapes of some common functions. Okay. And those common functions that I need you to remember are in the 2.2 notes, and 2.2 notes are here, okay? And so it's nice and summarized here, and this little summary page is going to be so useful, even if you go, or when you go into calculus, right? Having these shapes and just kind of knowing these shapes and what things look like is going to serve you really well. So it's worthwhile kind of looking at these and just approaching it like, well, I learned what a triangle looks like. Okay, so I can recognize a triangle. Okay, I learned what a root function looks like, right? An even root function, an odd root function, right? So we're just extending it. Oops. You know what? This is important enough. I'm going to put it on its own page, and I'll even scoot this down here because I ran out of room. Okay. And I want bigger. The only one that I'm willing to scrap on here is the greatest integer function, which is down here at the bottom, right? This is kind of optional. That's not one that I want you to kind of spend a lot of time on. It's really just rounding up your numbers to the nearest integer, which is a whole number. Right. Okay. So we already know a linear function, right? We know what a straight line looks like. And so here, it's a two-component learning thing, right? So you need to remember what the function itself looks like, right? Y equals mx plus b, okay? And then we need to remember, okay, so it depends on what the function is, right? So it depends on the slope and the intercept, but in general, we know what a straight line looks like, right? And so here, again, it's really important that you just kind of train your brain to think about, okay, f of x is really just y. So y equals mx plus b. We feel comfortable with that, right? And so, and we know that's a straight line, right? So if we're able to recognize the function of a straight line, then I also know approximately what it's going to look like, right? So before, when I said, oh, it's going to have a positive slope and then it's going to have a negative slope, right? So that's the cognition that I'm looking for. Okay. We've talked about quadratics, right? So power functions in general here is if you have x to the power of n. And what's interesting is that even polynomials, which are power functions added together, right? We've seen things like ax squared plus bxc. These power functions, or polynomials, as we call them, they'll behave like the highest power, right? So, which we call the degree of the polynomial, right? And so, let's talk about power functions. Power functions. I've seen quadratics, which have the shape or have the form of f of x, right, equals ax squared plus bx plus c, right? Notice that this is a polynomial, right? So here, this is a polynomial. Polynomial degree 2, because the highest power is 2, right? So the highest power of x is 2. So that's why we say it's a degree 2. Okay. And it's going to behave like the highest power of x. So overall, this shape is going to behave like the highest power of x. Okay. So overall, the shape of a power function will behave like its highest power of x. Like its highest power of x. Okay. So what does that mean? Well, it means we've already talked about this, right, in terms of the quadratics. Well, if my highest power of x is 2, then it's going to behave like a parabola. So if we go back to this little summary cheat sheet here, right, if you have f of x, sorry, it's so laggy today. If you have f of x equals x squared, right, then that's the overall behavior of this thing, right? It's going to behave like an x squared. Okay? If there's some things going on in the middle here, that's fine, right? So here I'm just kind of tracing the midsection. So it's really not keeping up today. Right, so there might be kind of some activity in the middle, but the overall general behavior is going to be kind of pointing up like this. Now, if you have odd powers, right? So notice that, okay, so here we have x to the 2, and here we have x to the power 4. So what we see is even powers of x are all going to be looking like a parabola. They just kind of squish down on the x-axis. Same thing with odd powers, right? But now x to the power of 3, x to the power of 3 looks like this, right? Same thing with x to the power of 5, except it's kind of sat down on the x-axis a little bit more, right? So what I want you to do is just kind of look at these and see, okay, how do things change? You can use Desmos, right? And you can map a few more of these, but in general, right? In general, if you have an odd degree, the behavior is going to be like this. If you have an even degree, it's going to look like this. So let's write that down. So in general, if you have an even degree polynomial, it's going to look like this. And I'm not going to do the midsection. I'm just going to do kind of, so here, anything can kind of happen middle there, but the end behavior is going to be pointing up like this. Okay. Remember if we've talked about, I think we talk about it a little bit later, but if A in front is negative, then it's pointing down. But let's leave that for now. In general, we're getting started with these shapes. Okay, so if you have even degree polynomial, it's going to look like up like this. And an odd degree polynomial is going to look like this. So we have kind of this upward behavior and then this downward behavior. And then here in between, things can happen in there depending on, you know, how advanced your polynomial is. Okay, so I'm allowing for activity here. There might be some kind of fluctuations in here. I don't know. Okay. But in general, this is the end behavior. And a lot of the time, it's the end behavior that we're interested in, right? What happens when x gets really, really small or really, really large? We even saw one, right? So from before, right? So for example, from the start of class, let me go back there. We looked at x to the power of 4 minus 6x squared plus 2 equals 0, right? Notice that here, okay, so we have this behavior here, but overall, right, my highest power of x is 4. So that's even degree polynomial, right? And so I'm expecting the overall end behavior to be up like this, which it is. Right? So we found that x to the 4 minus 6x squared plus 2, let me scroll down there. So from the start of class, we had x to the 4 minus 6x squared plus 2. We found looked like something like this. Right. And so here, my highest power is 4. Highest power of x is 4. So I am expecting an overall behavior like a parabola, right? Like an even power of x, right? An even degree polynomial, so I'm expecting it, sorry, this lag is driving me nuts. So I'm expecting it to look something like this. Right? So I'm expecting kind of this upward behavior, right? Like I said, I'm allowing for things to happen here in the middle. That's not really, we're not there yet to talk about what happens in the middle. We will. But for now, right, just knowing that, okay, well, x to the power of 4, I'm expecting it to go up like this, which it does, right? And then we said, okay, then there's some activity in the middle, which we can see on Desmos, right? But beyond that, we don't know yet what it looks like, but we will. Okay. Good. So let's take just a quick break because I know it's been a lot so far, right? But maybe just have a look at, and then we'll keep looking at the rest of these, but you'll start to see some patterns when we go through the rest of them. So let's just have a 5-minute break till 9:10. Good. All right. So let's see here. This, whoopsies, there. Okay. So these power functions, or in general polynomials, right, are gonna have this overall behavior of either parabola or this kind of S-style shape. Okay. Look at some root functions. So the nth root of x, okay, in general depends on if you have an even, so the square root or the fourth root, right? So even roots start at x equals 0, right? So the domain is restricted to being x is greater than or equal to 0. That jives with what we've been saying, right? We say we can't take the root of a negative number, the square root of a negative number. Notice that it doesn't exist, right? And so, however, if we look at the third root or the fifth root, right? Notice that we get a very similar behavior to what we had for x to the power of 3 or x to the power of 5, and now it's kind of going in this way, right? And so, right, noticing kind of the patterns here of even or odd roots is going to be really useful, right? So let's just kind of summarize that down below. So root functions odd roots, or sorry, let's start even roots because the square root is our most common root, right? So even roots in general are going to look like this. Oh, that's not a straight line, is it? Are going to look like this, right? Notice that it doesn't exist for x being negative, right? So here, notice the graph doesn't exist for x less than 0, right? Which makes sense because we can't take the even root of a negative number, right? Which which makes sense since we can't take the even root of a negative, right? So our graph backs up what we've been saying all along, right? And the graph is why we've been saying that. It's because the graph doesn't exist here. And so, okay, well then I need to remove all those values of x because they can't happen. Now for odd roots have a different behavior. So odd roots can take negative values of x because it looks like kind of in general it's going to look like this, something like that. Okay, and just like polynomials, anything can happen kind of here in the middle around the y-axis, y kind of origin, but in general the overall behavior is going to look like this. Okay. So again, so here, right, we can take the odd root of a negative. Since the graph exists for all values of x. Right, so that is the main. Okay, so we can kind of lump these up, right, into even and odd functions. Same thing with the reciprocal function. So the reciprocal function, 1 over x or 1 over x squared or 1 over x to the 3, whatever. Go back up there. I don't know if it's lagging. I'm assuming it's lagging as much on your end as over here. So annoying. Okay. So here for reciprocal functions, right, in general, 1 over x to the n, well, what pattern are we seeing here? We're seeing, okay, if n, so if the power in the denominator is odd, right, then we see this type of behavior, right? 1 over x is the most common one that we need to recognize. But then if n is even, right, then we're up above the x, right? Makes sense because if we're raising it to an even power, then all negatives become positive, right? So there's all these linkages that we can make, but we'll try to keep it kind of as simple as we can for now. So, okay, so, but that's how I remember it is, okay, well, if I have an even power in the denominator, then all my outputs are positive, and that's what makes it go above the x-axis here. X to the power of 3 looks a lot like 1 over x, except it's just kind of like smushed up a little bit more. And same thing, x to the power of 4, it's just kind of smushed on the x-axis a little bit more than 1 over x to the 2. Okay. So for reciprocal functions, if you have 1 over x to the n, right, that's a reciprocal function. If n, now I'll start referring to n because it gets a little bit confusing, right? If n is odd, then we have, in general, we're going to have this type of behavior. That. Okay. I mean, it shouldn't be lifting off here. That was just me being sloppy, but hopefully you're okay with that. And if n is even, right, then what's it going to look like? Then it's going to look like something like that in general, right? And just thinking about, right, all outputs are positive since 1 over x to the n is greater than 0 if n is even, right? If I raise something to an even power, x squared, for example, is only going to give me positive values, right? And so that's what's going on here. So we need to remember to kind of recognize those reciprocal functions. I am kind of speeding through these reciprocal functions because for us, they're actually not going to come up that much. And even in calculus, I mean, I do expect you to know what 1 over x looks like, for example, like this here. But in general, right, we can always use Desmos to see what these things look like. So the reciprocal function kind of lower on the list, but I do need you to know what root functions look like and in general what polynomials look like, and strings, of course. The last function that we're going to talk about and kind of know the shape of is the absolute value function. I would scroll up there, but it's really lagging, so I'll just start here. The absolute value function. The absolute value function. Remember, the absolute value basically takes any value and makes positive, right? Technically what it's doing, it's a piecewise function, and it's saying, okay, well, if x is negative, I actually take the negative of that negative, and that's what makes it positive, right? So what this looks like is the absolute value of x. So if you have f of x is the absolute value of x, which we just denote by vertical lines like this. The graph is going to look something like this. Okay. So if I have negative values of x here, then I map them to negative x, right? So which is a straight line with a slope of -1 with a y-intercept of 0, right? So here, let's remember that f of x is a piecewise defined function where it becomes x if x is greater than or equal to 0, and it actually becomes negative x if x is less than 0. Exactly. So if you have the negative, and we haven't really manipulated and transformed graphs yet, but if you do have a negative outside, right? So, or if you have fx is equal to the negative absolute value of x, then it becomes like this. Or maybe I should use that light blue color again. So the negative outside, a negative outside a function will flip the graph, I'll say kind of upside down, flip the graph upside down. Which actually applies to all of these graphs, but we haven't worked with that yet. So if it comes up, then just check it in Desmos and just make sure. But in general, that's what's going to happen. Awesome. Okay, great. And then, like I said, they have the greatest integer function on that little summary piece, but let's ignore that. I think we have enough functions to worry about here. Okay, and just remember that the goal of this, of talking about these functions, so that we're able to, oh, that looks like a root function. Oh yeah, it is. Okay. Or if you see a function and you say, oh, that's a reciprocal function, so I expect it to look like this, right? So, so that's kind of what we want for this section. Now, we talked about before, right? So here, kind of the end of this little blip. So laggy. So we talked about functions. We said a function can take an input x, any input of x, and it can only yield one output. So in order for an expression to be, or an equation to be a function, so we said earlier, let me write this down. We said earlier that in order for an equation, the difference between an equation and an expression would be, right, so here just note that ax squared plus bx plus c on its own, this is an expression, versus, and I'm just using the quadratic because it's equals 0, right? This is an equation. Only because I find that sometimes it gets confusing, right? But just know that, okay, if equal sign and it's an equation, right? If there's no equal sign and it's just something on its own and it's an expression, but they'll behave the same way, right? We can graph these, or we're just interested in where does it equal 0, right? Whereas the expression, we can just map that. In fact, I guess I should say an expression, kind of correct myself. So in order for an expression to be a function, each input of x, each input of x can only yield one possible output of y, right, or f of x, but you read those interchangeably, right? So how can we check this? So graphically, how do we check this? Well, we use what's called the vertical line test. So we can check if a graph represents a function, using the vertical line test. So I'm going to bring in the vertical line test blur. And maybe this here. So the vertical line test, and maybe that's okay. The vertical line test just says, okay, if you have a graph and at any point here, you're able to draw a vertical line and at no point do you cross the line more than once, then you have a graph, or sorry, then you have a function. Okay, so here, this is a graph function because at any point you can draw vertical lines, right? You can chop, 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 and you only get one cut into the line. Whereas here, right, this input of A, right, gives me two potential outputs. So the graph and this thing exists, but it's not a function. Okay. If you think about a circle, right? A circle, well, a circle is not a function, right? It's a graph and it exists, but it's not a function. Okay, so we need to be able to use the vertical line test is going to be pretty important. Okay, it's also how I give you kind of easy marks on a test. I give you a graph, and then I ask you, hey, is this thing a function? And then you either tell me yes or no, right? And how you're going to do that is you're going to use the vertical line test. So let's do a couple of examples here just so we can see what's going on here. And maybe I'll center this guy here. Match up. Okay. So it says, use the vertical line test to determine whether the curve is a graph of a function of x. If it is, state the domain and the range of the function. Now, I guess, so we want the range, but we haven't introduced it until 2.3. That's confusing. Anyways, the range is all possible outputs of y, right? So all the outputs of y. So here, if I go ahead and I draw imaginary vertical lines, it looks like I'm only able to intersect this graph once at each value of x. Okay? So here, let's do 53 over here. Is a graph or is a function by the VLT, the vertical line test. Where is that up here? Oh. There. Okay. So the domain of this thing, right? The domain is all the input values of x. It looks like it goes, so let's figure out the scale first. It looks like each tick is worth 1. And so from -3 to +2, including those values. And then the range, well, the highest value of y is 2, and the lowest value of y seems to be -2. For now, I just want to focus on if it is a function using the vertical line test. Okay, so because I'm about to talk about the range again, so just hang tight. Let's do 54, right? We already talked about circles, definitely goes for ellipses as well. So here, 54, ellipse. I think it's an ellipse. Doesn't matter. Swished circle. Here, well, it doesn't matter what value of x, in fact, that I pick here, I'm going to intersect the graph more than once. And so this is not a function. Not a function by the vertical line test. It is an ellipse. Thank you. I was thinking ellipses are also, aren't they the ... Or am I thinking of something else? words. Thank you. Driving nuts. Okay, the one that I want to really show you here is that, okay, so even though they look like a function, right, I want you to be fooled, because in fact here at x equals -1, you have this whole range of outputs, right? And so y can take on any value from, it looks like -3 up until +3. So it's not a function, right? And so here, 55 is not a function by the vertical line test, right? And I'll just do a quick explanation here. At x equals -1, we see y ranges from -3 to +3, right? So that's bad news. If we talked about, from -1 up till x equals 3, then yeah, it's a function, right? But it's this little section here that makes it not a function. Okay. And then here, right? So at each point, right, I can draw a horizontal line. The only one that I'm concerned about is here. Looks like it exists down here on this horizontal line, and then it jumps up, but it doesn't include on the x-axis at -1. Then it picks, and I'm able to draw these vertical lines again, right? So this is a function. So 56 is a function by the vertical line test, right? There's only one output at x equals -1. Great. So for identifying functions, right? Is it a function? Is it not a function? We can do it algebraically, so using math as well. It's a little bit more complicated. It is in the notes, but how I'm going to test you on it is just using the graph, right? So using the vertical line test, can you identify a function or if it's not a function? Okay, so let's briefly do section 2.3. There's not a lot in there, so that's why I want to kind of get it over with. So 2.3 is going to be, so I say there's not a lot in there. There's a lot of information in there, but there's not, most of it is kind of intuitive. So getting information, so 2.3 is called getting information from the graph of a function. Okay. So we already said that the domain is all possible inputs. So we already know the domain is all possible inputs. Inputs of x. Okay. So graphically, right, that means all the values of x that we can kind of have in our graph. Okay. So now we're going to talk about the range, which has already come up in that previous problem, but let's just pretend that we're introducing it now because we are. Just going to grab this here. The range is all possible outputs y. Okay. So the range is all possible outputs of y. Right? So from the graph, I can talk about the domain range. Now, it's until later in the course that I'm actually going to ask you to find the range like we have been finding the domain, right? So we're saying, okay, well, I can't divide by a negative number. I can't take the root, the even root of a negative. And so I can't divide by 0. I think I said negative number. It's not true. The old 9. So we've been finding the domain algebraically. Later, we will find the range algebraically as well, but it's a little bit harder. So for now, right, I just need you to be able to identify the range using a graph. Okay, so I'll make a note of that here. For now, I only need you to be able to identify the range from the graph. Okay. With some common ranges. Okay, so if you have common ranges include, so if you have a linear function, something like this, of course, this linear function has a domain that goes from negative infinity to positive infinity. Right, so here we have a linear function. They can have a positive slope or a negative slope, doesn't matter. But the domain here is from negative infinity to positive infinity, right? I can put any value of x into the linear function and get an output. And also the outputs go from y equal negative infinity to positive infinity. So the range here is also from negative infinity to positive infinity. How about, let's talk about quadratics or polynomials. Polynomial functions. If you have an even degree, right? An even degree, then remember the function looks like something like this. And it would be flipped upside down if the a in front was negative, right? So if the first coefficient or the coefficient of the highest power is negative, it flips it. We're not there yet, but we mentioned it earlier. The domain here, I can put in any value of x and I can get somewhere on the graph, right? So here, the domain is still negative infinity to positive infinity. And you know what? The reason I'm hesitating is because we saw where it kind of dipped down. So maybe what I should do is I should just talk about x squared. Let's talk about just specifically x squared, not just an even degree. Because it kind of opens a can of worms I don't want you to have yet. X squared, for example. Well, this should be kind of more rounded. Oops. Right, so the domain, I can put in any value of x in it, and it just keeps going and going, right? So even though it doesn't look like it, these arms actually extend to negative infinity and positive infinity. Here, our range, we bottom out at 0, right? So the lowest possible value of y that I can get for x squared or any even power is right? So it starts at 0, is from 0 to infinity. It includes 0, right? 0 squared is 0, it exists. Or if we have x to the power of 3, right, something like this. The domain, again, is negative infinity to positive infinity. And the range now, there's no restrictions on the outputs because all of them are covered entry, so it's also going to be negative infinity to positive infinity. Okay. So you can go through that list of all the functions, and just looking at the graph, you can see where what your domain and range are. Right? Let's talk about maybe roots. Let's talk about the square root of x. The square root of x looks like this. Oops, looks like this. Right? Even though it doesn't look like it here, this actually goes all the way up, right? Because we're extending this to infinity, so and beyond. Right, so this is going to go up, 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 and it will reach infinity at some point, right? It's going to bottom out at 0. I can take the root of 0, 0. So the domain is from, including an input of 0 to infinity, but also the range is from 0 to infinity. So those are just some common domain and ranges. Okay. Okay. So looking at the graphs, there it is. What I want you to do is just go ahead and graph these things, and maybe what we'll do is let's do the last problem together in Desmos. So whenever you see this little kind of graphing calculator dude here, you should be using Desmos, right? So as soon as it mentions anything about, oh, use a graphing calculator, use Desmos. Right? You don't have to have a graphing calculator anymore. So let's do 22 together, just because it has this negative up front. So, and let's just see what that thing looks like, okay? And so if I asked you to find the domain of this thing, you would say, well, 25 minus x squared can't be negative because I'm taking the square root, right? And so we already know what the domain of the thing is. It's 25 minus x squared greater than or equal to 0. But let's just graph out in Desmos. So 22 in Desmos, right? So here, I'm just gonna highlight this here. Use Desmos for sure. Whenever you see that little guy. Okay, so I'm gonna graph 22. So I have the negative root of 25 minus x squared, all under the square root. Make sure I copied that down right. Okay, good. It looks like I have nothing here, but now zoomed in on the graph I am. Okay, so when I zoom out, now I see that, okay, there is this kind of half a circle going on. In fact, it's the underbelly of this ellipse. And so it looks like, okay, the range is going to be from 0, right? So it's including those 0 points on the x-axis, and then it's going down, and it looks like this is the bottom of this thing, right? So the lowest possible value of y is -5. And just like we said, right, we would have found that the domain is going to be between -5 and 5, right? 25 minus x squared has to be greater than or equal to 0. We see that here, -5 and 5. So from the graph, so here we find, let it catch up here. That it's something like this. Okay. And so here, this is at -5, this is at 5, and this is at -5. So then the domain we see here, we could have calculated it as well. In fact, if you calculate it, you should check it in Desmos. The domain is from -5 to 5. It can include those values, whereas the range is from, now it seems to be including these values if you kind of convince yourself, well, if x is +5, for example, 25 minus 5 squared, how do we know that it includes these? It's because you can have 25 minus x squared, it can equal 0, but also when you graph it on here, if the value wasn't included, it would say, it would have an empty circle. I know that's not super clear, because sometimes you can't see it, or often you can't see it. But because this is just square root, I'm allowed to be at 0. So sometimes we have to do a little bit of math, but not bad. Awesome. So then the range, because I'm allowed to be on the x-axis, well, the x is at y equals 0, and then it looks like it goes down to -5, including -5. So it goes from 0, including 0. Oops, sorry. I almost went from 0 to -5. That doesn't make sense. -5 up to 0. Always have to be increasing on a number line, right, in your interval. Otherwise, it doesn't make sense. Not sure about if it's including these endpoints, right? Plug in the values that correspond to this. So here, this looks like when x is 0, while the root of 25 minus 0 is 5, so -5. Okay, it is including that point. Sold. So I know I'm out of time, and we'll keep talking about, but just try those, the rest of these in Desmos, just to kind of get an idea. And let's, and then we'll do maybe 18 to start next day. Make a note to myself. All right. If you have any questions, let me know. Otherwise, I'll see you on Thursday.